Great. Okay, so welcome everybody. My name is Louis Powell. I'm Director of AI Technologies at the GSMA, one of the proud sponsors of the AI Telco Troubleshooting Challenge that we launched a couple of weeks ago. Today we have some special guests from our technical advisory team at AT&T. We have Mark and Farbod who will take you through the business justification and the.
They have the slides, or we have to flip it up.
I've got the slides. You guys, we can hear you, by the way. Yeah, so we've got Mark Austin, Vice President of Data Science at AT&T, and we have Farbod. I'm not going to pronounce your name, Farbod, because I didn't practice that beforehand, so you have to tell the group. Data Science at AT&T. They will take you through the business justification and the sort of reason, the work that AT&T have been doing on troubleshooting and benchmarking what they've done previously. And then Farbod will also go through a technical deep dive of the code that's been made available in ordering for participants to train their models on the provided compute. So we'll do that for about sort of 45 minutes or so, and then we'll have time for questions at the end on the general competition. We have various different members of the core competition team, so hopefully we'll be able to answer any questions you have as a group. As I say, this is being recorded and it'll be available to share afterwards, but please use this opportunity to ask the team any questions you have, and we will send follow-ups afterwards. Okay, with that, I'll hand over to Mark. Are you okay to share?
Yep, very good. Or what should I put it, or you want to do it?
You can.
Okay. All right. Well, it's good morning for us, and maybe good afternoon, good evening, depending on where's everybody at. Can everybody see our slides? Are they sharing?
Yes.
Okay, great. So I'm going to go ahead and start off, and of course I'll give you a little bit of the business reason for this, and then Farbod's going to go through how to actually train a model to kind of predict the root cause. So of course at AT&T we operate both wireless and broadband networks, and one of the problems that sometimes people encounter is low throughput. Okay, so you're trying to download a web page, you're trying to stream something, you might get pauses, you might get jitter, and so that's kind of a common symptom in terms of what you might encounter. And the basic question is there a problem that we can fix? Is it a short-term fix? Is it a medium-term or a long-term? Now, in general, there's probably thousands, or depending on how extent your network covers, could even be into the millions of these things happening, depending on where people are at. But the basic concept is you'd like to predict the root cause, and we'd like to collect these incidents, and we'd like to get a way to predict the root cause. So the nice thing is that it turns out that just like a human would reason through looking at the data, and the data in this case could be, well, let me look at the data from the cell sites that are serving it, and let me look at the drive test data, let me look at the configuration, and try to reason through what actually was the issue. So sometimes those come across to us as tickets, somebody's a complaint, or sometimes you just want to collect those things and proactively figure out what are the issues and to what extent is the problem. So like Lewis says, the GSMA recognize this as kind of a general problem and put together a task force to actually come up with a example benchmark. And the basic question is, can we use a large language model to predict the root cause for these low throughput problems? And the benchmark data set in this case is synthetically generated, and it's around 2,500 samples or so, Farbod, I think. in terms of what you'll have access to. And the basic format that you'll present the problem to is as you see on the page here. Okay, so the basic question is, as you see there, is, analyze a 5G wireless network, drive test user plane and engineering parameters, and identify the reason for throughput dropping below 600 megabits per second. Now, in reality, depending on what kind of network you're running, in some places that might be a very good throughput as it is, 600 megabits per second. But in some cases, if you're really trying to get very tightly, close cells together, you'll have targets like that. But regardless of whatever it is, the basic concepts are the same. So in this case, we're defining low throughput as dropping below 600 megabits per second. And what we're trying to predict is one of 8 root causes. And you can see those labeled as C1 through C8 there. Okay, so one of them could be the tilt of the antennas is too large. Okay, so and that kind of alludes to a potential fix as well. Well, if the antennas are tilted down too much, if I tilt them up, I can point more signal to that user, and I can improve the coverage, and their throughput will go up. Or the serving cell's coverage distance exceeds 1 kilometer, resulting in overshooting. But anyway, in each one of these cases, these root causes, you can kind of see the description. Now, what do you give the large language model? Is kind of the same thing you would give a human. You give them what is the default. So what is the default tilt of the antennas? And what is the characteristics of the antennas that you see there as well? And then you give them the details. Now, the details, I'll just flip the slide here. The first thing you give them is the user drive test data. And that looks like this. So the first part is, think of these like all the columns. And you notice they're pipe delimited, timestamp, lat, long, etc. And then you get the actual data. Okay, so the same format below, you'll get all the data as well. Okay, so think of those as drive test data. So if you had the ability to drive test, that's what you would see. And then the engineering parameters is more off of the cell site itself. Okay, now the training data that you're going to see, remember, there's one of 8 root causes, is you have to, if you present this, what is the actual root cause? Okay. In this case, the final thing that you'll see in the training set is you'll see, in this case, it's C3. And if you go back up here, so C3 is a neighboring cell provides higher throughput. So what it means is there's, for some reason, probably parameters, is that you're not on the right cell site. You should have been on the neighboring cell site, which has higher throughput. That's kind of the root cause. Okay. So that's what the data looks like. And what Farbot is going to go through is he's going to kind of tell you, we'll show you some actual code. I think you're actually going to run it as well so you can actually see it. He'll actually show you actually predicting the root cause of this, much like a human would do. And for some of you may be familiar, he's going to go through a method called LoRa. And LoRa is a way, if you take an existing large language model, you tune a portion of it. Okay, so if you were to look at over here on the left, if this represented all of the parameters of the large language models, and remember, depending on the size of your large language model, it could be anywhere from hundreds of millions of parameters to, if you look at the GPT-4 or some of the other stuff, those are like in the trillions of parameters. We're going to be mostly looking at smaller models, but in any case, LoRa is that you're not tuning all the parameters, you're tuning a portion of them, and the parameters themselves we have them remain fixed, and you add in a portion which is represented in blue here. These are the ones that you're actually going to tune. Okay, so the code that you'll see will actually tune this, and then you will add those together onto your model to come up with a prediction. Now you won't see the final output is going to be reasoning through one of the 8 solutions there too. So that's the concept. Now, what Farbod's going to show you is there's still lots of things you can try, okay? And he's going to explain what all these kind of notations mean here. But there's different layers and there's different parameters within the large language model that you can tune, and that's represented by all of these things that you see in the middle here. Okay, so he's going to talk about the Q projection, the V projection, or all, QK, VO. All these things are going to be options. So these will be options. There'll be learning rate options. There's a lot of knobs that you can tune to try to get the best actual solution. Okay. Now we just put this in here. This is some idea of what you could try. Okay, so we have a little bit of rules of thumb. So you might start with the Q projection V. That's the best mental improvement at the lowest cost. So if you got to get something working, and you got to get something that you can tune quickly, you might start with that, and then you could throw all of them in there at some point, depending if you have the right computation and time to tune it as well. But the concept is you're going to be tuning a portion of the model. You're going to be trying to get the best classification of the output. Okay. So I'll turn it over to Farbod, but if there's any general questions, happy to answer any general questions as well. Let me just say one more thing. The way that we think about this is that this is a perfect example problem, and it's an example problem on a synthetic data set. But the concept is if you can solve this, you can easily load in real data, and you can actually show it, and that's what we're doing at AT&T, of course. And you can use the same approach for different problems. So we're looking at low throughput. Of course, other common things you could look at is dropped calls. So you could say, try to predict what's the root cause for a dropped call. You could predict, what's the root cause for, I couldn't get on the network to begin with, could be another one. But there's a variety of different things. But the nice thing is you're seeing the perfect example with this synthetic data set. But if you can solve this, you can apply it to real world problems. That's the important thing. Okay. So if there's no questions, I'll hand it to Farbod and he'll show you actual example.
Awesome. Thank you, Mark. All right. So Mark just described what does the input of the data look like, and in order for you guys to fine-tune the model, you can decide on the format of the output depending on how do you want to fine-tune the model. So you have control over the output. Essentially, whenever you look at the data, you're going to have the input as it is, which will be provided to you. So you can use that as it is. You don't necessarily need to modify it. But the output of it, it's really, really up to you. You can go directly from the input all the way to just the output as provided, which is going to be just a class that you're predicting. Or you can provide some guideline or some sort of reasoning trace. And it's a variable. It's a experimental, empirical thing that you will need to justify how you want to actually fine-tune the model. Once you do decide on that part, and we will share all of this with you as a README file that you can actually see what the input should look like and what the output going to look like, to have a example for you guys to basically work off. But assuming you have a test data, the way that I just described, there are multiple hyperparameter that you can modify that would affect the training. The very first one is the max step. you can look at the max step is essentially in each epoch there are multiple steps that your model train. Each step is basically defined as when your token goes through all the models and your gradient gets updated. So that's one step. And how many steps do you want to train? It's really up to you. You can start with 100, with 200, and see how well your model perform, and then you can increase or decrease it as needed. Another metric that affects the training significantly is also learning rate. How small do you want this number to be, or how large do you want it to be? It's really up to you, and you can go over this as a empirical and experimental thing as well. The batch size is a part that is really like you is limited to the number of GPU this model is deployed on and how you fine tuning it. We will provide some guideline for the batch size because the combination of the batch size and a max token block size together affect the memory available on the node that the model is deployed on. Essentially, it's not like you can increase this number to 64 and increase this number to 8,000 and it's going to work because there is a limited number of compute available for every single model, and the combination of these two really affect the memory available on each GPU during training. And these four are arguably the ones that affect your adapter that you're training significantly. As Mark described, these are the hyperparameter for LoRa. And you can actually see you can modify R, which allows you to justify the number of parameter that you're fine tuning. The higher they are, the more parameter you're fine tuning. So let's say if it's R8 versus 16, in 16 you're fine tuning twice as much parameter. And the rule of thumb for alpha is usually twice R. So whatever number you decide in, make sure to just have alpha twice. And you can avoid having a LoRa dropout. It is recommended to have some. And this is the part that Mark was just showing you in that table. You can also decide what part of the architecture you want to fine tune. You can maybe only fine tune the multi-layer perceptron layer, which MLP, which then you have to target these three keywords. Or you can fine tune the attention layer, which you have Q, KV, and output. Guess it might be helpful if I show you this. Essentially, imagine this is the entire architecture of a transformer or of the model you have access to through an API. You can either fine-tune the multi-layer perceptron, which in that case you're targeting this layer, or you can fine-tune your attention layer, which in that case you're targeting Q, KV. Which one would work better? Which one essentially, and I also no one is stopping you to target all the layers. So you can simply, these are the choices you have, and by default you're only fine-tuning the attention, but you can pass all of this as you wish, and it's not necessarily 100% guaranteed or predictable that what's going to work better. So it's empirical thing again that you might need to give it a shot. But long story short, these are the only hyperparameter that you need to modify before you submit a job to the model API for fine tuning. And remember, you have full control over how the output of the model would look like. So whatever the output you want to, like in whatever format you prefer, plus this hyperparameter are the only variables in a fine-tuning job that you can modify. Once you go over this, once you decide how you want to set each parameter, the rest of the code is in a fairly good shape that does it automatically for you, but I just want to explain it briefly. Every single model has certain special tokens that would add it before and after the input prompt and before and after the final answer. And that's the part that is essentially code is doing here. On your training set, you want to make sure the model understand then when the user is starting, which is basically the input prompt, this is what is provided to you, and you actually want to make sure the model understands when the output starts. And it's in this example, we are going directly from the example, which is this, all the way to the gold label. So there is no so-called reasoning trace. We're going directly from the answer to the category that is being predicted, which is a relatively simple way to do it. And then what we're doing here basically in this part of the code is we are attaching all of the training points in one data set, and we are submitting this data set through an API to the model for getting trained, which is going to be down here. You guys really don't need to modify any of this. It is going to work by default. It's just a standard way of distributed training. So and your logs is going to saved in the environment that you're working on, and I will show you momentarily what does that look like. But before I show you guys one like a live experiment, do you guys have any question regarding this hyperparameter that you can modify? Perfect. So now that you have this, you can submit a job by simply having all these parameters set and having your data ready. You do a python train.py. There will be a README file shared with you with this GitHub repository, so you don't have to memorize anything right now. But once you submit a job, you immediately get a JSON file like this, which it's a config of your job that you just submitted. There is something called model ID. This model ID, this ID is very important. You need to copy paste this, and you can actually see what is the status of your job. You do a scalar LLM logs model equal that model ID that you had over there. And then you can actually see the model is going through, it has loaded the model. There are multiple GPU. On each GPU, we are submitting the job, and you can actually see the model is getting trained. We have you are at step 20, step 21, and if you remember, I put 52 steps. So the model as we speak is getting trained, is at like 31 a step. You can look at the logs. There is so many things in here that if you are interested, you can take a look. Essentially, you can see as it starts, you can see how many GPU it's running it on. There's gonna be like the config file that you have that is being submitted, which is basically your LoRa alpha, LoRa troop R, and the layers you're targeting for fine tuning. This is all available to you. You can also see the model that is being used. There are gonna be 3 links provided to you that you can switch going from QN 2.5, 1B, 7B, all the way to 32B. So you have an option to fine tune whichever you want. We will provide some guideline like the larger the model, the more memory it gets, so the less basically available RAM you have for training. But long story short, you can actually see we just fine-tune a model for 51 steps, and on average took 1 second per step, and the model is already have been saved, and we are over. As you can see, like it's significantly fast to train a model for this. So I would expect, even if you use all of the data, like everything that is included for telelogs, and it should not take more than 10 to 15 minutes per model to train. So in one given day, you might be able to train 20, 30, 40, 50 different models. And that's the benefit of this being an experimental thing. So now let's just go out. Now that the model is being trained, you can use your own fine-tuned model to inference. All you need to do to get this ID again, and you can inference from your own model. Not only you know when the model was trained, now also after you inference from it, the result of the inference is going to be saved there. Assuming you modify these two, and we will provide a few guidelines for the max token, but pretty much you only need to like change these four. This one will always take you to the data that you want to use for validation. For telelogs, there's going to be two sets. One is training, one is validation. Training, I believe, is 2,400 training points, and for validation, you have 864 or something. So you don't, once you set this up, you never have to change it because your validation set, it's a separate set anyway. Essentially, you only have to like modify the model name, which every time you train, you get a new ID. The run folder, which is essentially the latest one, the latest model that has been saved. Once you have this, then what you would do is you inference from the same model that you just fine-tune. And this is a very small example of inferencing, so it should take pretty fast, but you can see I was able to inference in batch size of 2, and each time it took approximately 1 second. And then the result is going to be shared here. And you can actually see for, this was the question. This was what we sent to the model. This is basically what we inference from the model. And this is the answer that was given back to us. Whether this answer is correct or not, it's a whole different story. You need to verify it, but that's how you can actually inference from your own fine-tuned model, and then you can actually verify it to see if it's working any good. Arguably, if on those 800 examples you're at a certain accuracy threshold, you can actually compare your solution with other folks, and yeah. That's pretty much it. So you can submit jobs and then you can inference from it. Any question?
Can you show it just running an inference and show the reasoning?
I just did.
Okay.
I just
compared to the GPT-5, the comparison thing?
Oh no, I don't have that.
Okay.
But I can you just want like a live inference, the fine-tuned model versus ChatGPT. Okay. Well, there is a experiment I can run really quick. You can actually see once you fine-tune this model, it is a lot faster than any frontier closed source model when it comes to inference. And let me see if I can run one quick experiment for you. All right. You're not expected to do this part, but I think it's a good indicator how fine-tuning can help with this benchmark, and also how fine-tuning can help overall in telecom. Okay.
Let me show this real quick if I can.
Okay.
Now the reason we're excited about this, let me show one slide here. Is you can get amazing performance out of this this fine-tuned model. So this is the one that we did here on the left. So this was not with Quen. This is with Gemma 3. I'm really interested to see what you guys do with Quen. Is it sharing?
It is showing, but it's like split like this. It's not the whole screen.
Oh, it is. Okay.
Yeah.
Okay. Yeah.
That's fine, Mark. We can read it like that.
Yeah, so we're really interested to see what you all do, because when we did it before with Gemma 3, you see we beat GPT-5, we beat Grok 4, we beat Claude Sonnet 4.5. And this is think of this as the percent that you got the root cause correct, right? So that's C1 through C8. It's coming in at a little over 80%, correct there. So that's what you can expect to see. But I would also use that as like your guidelines is like you should try to beat that, right? Because that's kind of the basis there. Okay. Now it should also be a lot faster, and I think that's what Farbod's going to show here. We'll show you side by side. Again, you don't need to do this, but we're just kind of illustrating. So one reason to do it is get better, get more accurate, and then get cheaper. So it's a fine-tuned model. And then the last one is it should be a lot faster too, since it's a much smaller model. And I think that's what Farbot will show here.
Okay, let me just give you guys a very quick. All right. So this is it's just basically an experiment we ran a while ago. I just want to like run it for you. So on the left side is the fine-tuned Gamma 3-4B model that was generated from that we fine-tuned a while ago. I'm inferencing on the left side from the fine-tune. On the right side is GPT-5. And as you can see, it takes a lot of time for GPT-5 to even start generating anything. On the left side, we are already over. We inference from the model. We have the final response.
C3 on the bottom there.
Yes.
Right.
C3 is the response, but we are still waiting for GPT to generate something, GPT-5. And now GPT-5 has started generating tokens, which is just the answer to that given question. And it's this example was, it's one of those examples that the GPT-5, even after so much delay, is getting it wrong. And that's the power of what you guys can do with fine-tuning a small language model.
Yeah.
And hopefully, and this is how we decided, but like there is so many different other ways that you can actually fine-tune this model, and it can outperform closed source models actually.
So beat the 80%. And then if you want to do that for fun, you can kind of compare it to that trillion parameter. I mean, nobody knows exactly, but it could be trillion parameter compared to 4 billion.
Perfect. Well, thanks, guys. I really appreciate that, both of you. I think that's a really good deep dive, both into like how AT&T is so excited about this and the work that you guys have done already. So next step, Farbod, you'll share the code that will be available, and teams
Yes.
will be able to start running or training their models as of next week. Yes.
Yes.
Do you want to talk a bit about the capacity constraint on the compute?
I believe it would be very helpful depending on how many teams are planning to use this, Luis. If they start using it one at a time, you can submit jobs and it's going to be a queue of jobs, but there is a limited compute available depending on the model. I believe the largest model has 4 GPU, 7B has 2 GPU, and the 1B model has 1 GPU allocated to it. So if one person uses at a time with the instruction that we provide, is going to be a lot more efficient than everyone trying to hit the same endpoint at the same time. So I will let you decide the schedule of team accessing the model. But as I mentioned, you can train a model on the entire data for any of those models, regardless of the size, in 10, 15 minutes at most. So you can train like 30, 40, 50 model in one day and inference from it. And so 1 or 2 days of training, it's a significant amount of time that people can and can train a lot of models. Does that make
Great.
sense?
Yeah, that makes sense. So for the teams on the call and watching this on playback, get cracking soon. We will be working as a core group to allocate teams and giving them allotted times, because there's been a a big influx in participants, which is great news, but we need to make sure we manage the compute. So bear with us as we start to allocate that over the next couple of weeks. But at the moment, next week you can start get cracking, and then we will sort of allocate you. So yeah, please bear with us as we make sure the compute resources are used effectively and reduce any complaints. I think that's covered most of the things we wanted to focus on today. Are there any questions from the group on topics either covered just now or in general about the competition, the platform, the data, the competition, the prizes, etc.? Then now's your chance to ask. If not, we probably will be running some type of update webinar, in the new year, just to see how teams are doing and answer any questions. And now is a good time to ask anything that's burning. There's a couple of people typing, so we'll just wait to see. There's a question from Joseph. Can we apply other training methods?
Can they apply other training methods? I think so, right?
You could apply different training method, but you should modify the ML directory significantly. And it's as long as you're comfortable writing PyTorch code, you can do it, but then it requires I guess the easiest way is to just modify LoRa, but it's the PyTorch code. Like the sky is the limit. You can apply any algorithm you want, but it requires debugging. It requires testing to make sure it actually works. And we are using something like supervised fine tuning. So we do have an input and we do have an output that we have already defined. And we're the only I guess part is we are only fine tuning a fraction of the parameter, just to be efficient. We're not like essentially fine tuning all the parameters.
Yes, so I think just on the can you apply other training methods, that yes, you can. What AT&T providing is a way to approach things. But as a competition submitter, you don't have to use AT&T code. You just have to use the models, and you can use whatever approach you want. We just thankfully have the AT&T sort of cheat sheet or a nice set of APIs and code to give you a head start. But if you want to explore other methodologies, I'm very keen to hear from you as well. Can we train? Oh, go on.
I think, Luis, that's a good question for you. I think I guess the bottom line is if they want to generate their own data, synthetic data on top of that.
Yes.
I think the way I would think about it is it's possible, but at the end of the day, it's still going to be graded against the holdout set.
Yeah.
So, I mean, you can, to the extent that you think it's going to help you on the holdout set, then that's fine.
Exactly. So yes, but ultimately you're judged on the private set. Yeah, the holdout set. Any other final questions? Nope. Okay. Well, I think we'll take a pause there. As I say, the recording will be available for you to watch back later. I think once you get your hands on the code as well, that would really help. Mark Farbob, we thank you so much for your time today. We might come back to you later in the new year once we get a sense of how many questions we have from the teams, and maybe we can do a sort of another session as people have explored the data a bit more and maybe have some further questions.
And Lewis, I don't know if we shared our emails, but you're happy to share those with the group. They can get in touch with us if they got any questions too.
Perfect. Okay, I'll do that as a wrap up.
We'll run them past you, of course. Your ultimate, but that's fine too.
We go direct to you. Great. Okay. Yeah. Well, what we can do is we can post them on the Zindi platform, and we'll just specify about technical questions and reach out to you. If not, they can come to myself.
Yeah.
Okay, brilliant. All right, well, thank you so much for your time. Really appreciate it, and looking forward to what the teams come up with. If you do have oh yeah, we've got a final hand up. Or was it gone? No, okay, it's gone. Yeah, looking forward to what the teams come up with. You know, the AT&T guys have done a really good job. They set out a tough benchmark for you to exceed. So looking forward to seeing the work you can do, and hopefully we'll get to meet you in Barcelona at the prize winning. So best of luck to everybody. Thank you so much, and have a great rest of the day and a wonderful weekend. Thank you.
Yeah. Good luck. Good luck.
Thank you. Bye. Bye.